Okay, in the last section we talked about ionic bonding and indicated that if a compound was ionically bonded, it definitely had implications as to the strength of that bond and to properties of the compound. In this module, we'll just look briefly at a couple of other factors that might influence the properties of a compound. First off, in the ionic compounds, we noticed that they were lattice, and here's a better picture maybe describing or showing a lattice structure where perhaps this is a sodium here, so all these are sodiums. Maybe I'll pick this sodium right there. And this sodium here is attracted to this chlorine and this chlorine and this chlorine and the chlorine down below it, and there'd be one out front here too that it'd be attracted to. And that contributes to the strength of that particular compound. Here's a picture of a crystalline kind of structure that would be ionically bonded. Now there's other things that could affect them too. For example, here I have lithium fluoride. If I have the compound lithium fluoride, this is a metal, this is a nonmetal, it's an ionic bond. I look at the properties of that ionic bond. The melting point is 845 degrees Celsius. It boils at 1600 degrees Celsius, like an extremely strong bond. Like it takes a whole lot to start breaking up that compound. Whereas I look at another fluoride, and instead of lithium fluoride, it's the atom or the element that's just right above lithium. You'd think it'd have similar properties, but it's hydrogen fluoride. And hydrogen fluoride, we know from tests, does not do an ionic bond. Hydrogen we don't really classify as a metal. Typically it's classified as a nonmetal. So it's not an ionic bond, but it's a covalent bond. And look at its melting point and boiling point. Just a huge difference between those. And so if something is transferring electrons like an ionic bond versus whatever a covalent bond is doing, that has to be some kind of difference. It must be doing something huge to make that much of a difference in the melting and boiling point. Other kind of factors other than melting and boiling point that we can look at are also things like solubility. Typically ionic bonds or things that bond ionically are quite soluble in certain substances and not soluble in others. Another factor or property that we can look at is reactivity. So when we compare all of those, what we're doing is we're looking at the interactions between atoms. And sometimes we can transfer electrons like we do with ionic bonds. Sometimes we share them, as we'll discuss later, as there are with covalent bonds. When we look at the whole continuum, though, of bond strength and attraction strength, this is sort of the continuum that we have. We have ionic bonds, very strong, stable kind of bonds. We also have covalent bonds. So these ionic ones are ones where there's a transfer of electrons, and here there's a sharing of electrons. And here the range of compounds or melting points, boiling points, those properties, quite a wide range of that. Whereas like a covalent compound could be found as a solid, liquid, or a gas. Whereas ionic compounds are all solids at room temperature. But those are the two extremes. We'd also have bonding or attractions between elements that could be found anywhere along this continuum. And what we're going to play with a little bit for the rest of this module are looking at polar covalent and versus covalent bonding. And we'll look at maybe some factors that might place compounds somewhere along that continuum. Okay, so we have ionic bonds, we have covalent bonds, but there are also other types of bonding in between those. So I can't say it's ionic has all these properties, covalent has all these properties. It doesn't work that way. Certainly we have ionic and covalent, but there's a range of properties and a range of strengths of those bonds. Okay, one other factor that contributes to that range or that continuum that we were just speaking of is something called electronegativity. And electronegativity is something that tells us how much an atom or an element is looking to get electrons. On your periodic table, most periodic tables have these numbers listed. And they're just it's a relative kind of number, where here hydrogen, its number is 2.2, that's its electronegativity, and here lithium is 1. So I would sort of assume maybe that hydrogen would like electrons more than lithium. Look at some other ones. Oh, here's fluorine. Fluorine, its electronegativity is 4. And if you look on the periodic table, I'll just pull it up quick. If you look at the periodic table, you'll find that fluorine is the top dog. That's actually the one that we compare all the rest of them to. You look anywhere else, I've got 3.2, 3.4. Those are some of the higher numbers. But then you look in terms of electronegativity, and the electronegativity seems to increase going this way and seems to decrease going this way. In other words, the guys sort of in the top right want electrons, desperate for electrons, whereas the guys in the bottom left don't want electrons and in fact want to get rid of electrons. So what happens then if I have maybe an element here and here? Would that be a different kind of bond than maybe an element from here and over there? So would that be a different kind of bond? Would that find me in a different part of that continuum? And certainly it would. So electronegativity has a role to play in the property of elements. When we look at the difference of electronegativities, like here fluorine's 4 and francium's 0.7, some scientists or some chemists have sort of given a general continuum. And again, it's identifying 3 points, but there's more than that. But anyway, it's a general guideline that can help you determine what kind of compounds you have. And here it is. If I have the difference in my negativity very, very small, very, very close to 0, the kind of bond type that forms is a non-polar, we'll talk more about those later, covalent bond. An example would be oxygen or nitrogen or fluorine, any of those ones where they're diatomic, so the difference in the electronegativity would be minimal. If I have a little bit of difference, up to about 1.7 is the number that they typically use. Up into that, I have a bond called polar covalent. Typically those are ones where the electrons are being shared. An example might be hydrogen fluoride. Other example might be water. That's another example of a polar covalent bond. Now, if the difference in their electronegativity number is greater than 1.7, then typically I have a whole transfer of electrons, and I have an ionic compound that's formed. So sodium fluoride or sodium chloride or calcium sulfide. Lots of different, typically any ionic compound is going to have an electronegativity greater than 1.7. Okay, so we've discussed a few other kind of things that we can use to determine some properties of compounds and determine what kind of effect these properties come from. Like, do they come from an ionic bond or do they come from a covalent bond? In the next Scribblecast, we'll look more at this idea of polar and non-polar covalent bonds and what kind of effect they have on the properties of the compound.